Alright, hello and welcome back to Tomography. So slightly different setting, you're seeing the other side of my office. I just finished recording a MATLAB session for my numerical analysis class, and so I just wanted to go ahead and take an opportunity while I had it to go ahead and start recording for you guys. I'm sorry if some lectures have been slow in coming lately. I got one solid one out last time, which we actually tied everything back between the Fourier transform and the radon transform. And I've had an exam to give numerical analysis, how to get that graded, had paper reviews I had to do, I've had grants to write, and all these other things, which put me a little bit behind, and I do apologize for that. But hopefully you're able to fill in the time with going through and looking at some of the interpolating the trapezoid rule and the Simpsons rule for numerical quadrature, which we'll need for the next project. The project that you have right now, I'm collecting it this Thursday, and if you haven't, go ahead and send me an email with it, and if you're having trouble with it, just take your time. It's a small class, and so I can be flexible. So if you need more time with it, no big deal. Just keep working on it, and that'll be okay. If you take a look at Feynman's book, second edition, and the radon transform chapter, I'm just asking you to go ahead and follow what he's doing there as far as rotations and translations for the radon transform and getting explicit formulas. So it's not too bad. And if you can't do that, if you can just merely do what I've already demonstrated in the last video where I was coding up and demonstrating how to use the radon transform function in MATLAB, that's fine too. I just want you to be able to play with this stuff a little bit, and then so you're comfortable when we move on to the next project where you're actually going to be doing a lot of this Fourier transform stuff by hand. And so now I've mentioned the Fourier transform, why don't we talk about what we're talking about today? So if you looked at last time, I showed you how we can get this whole filtered how we can get the filtered back projection. Sorry, I want to say propagation, but that's something on neural networks. Anyway, so the filtered back projection is basically is called a filtered version of the back projection. So then the question is, what is this filtering? And so if you look at there, you see you have the Fourier transform of the radon transform getting hit by the absolute value of the frequency, which was capital S, and then you're being inverted back, and that's called a filtering. So basically what you do for a filter is you take a function and you take its Fourier transform, and then you multiply it by something else, and this ends up being what I would like to call a multiplication operator from my own perspective of my dissertation, but in general it's just called a filter, where it sends one function to another one after you finally invert with the Fourier transform. And so the filters are used for extracting different kinds of information out of your function. And one thing that you can do is you can do noise filtering, which is really kind of where it gets its name. So the idea is that if you want to truly extract your signal from radon transform, then you need to do this filtered back projection, and it's it literally written, that's exactly what you have to do, is multiply by this absolute value of the frequency. But in truth, it actually will amplify your noise considerably if you have any noise. And that's because noise tends to be high frequency, and when you multiply it by the absolute value of S, you're zeroing out any zero frequency noise, but you're amplifying anything that is higher frequency. So as S gets larger, you hit your high frequency content, but then you're multiplying it by S again. So it gets to be a lot larger. So so in practice, you don't actually use that literal filter back projection in the process, but use that as a way of starting. And so what we're going to do is we're going to combine this, what is called, with a bandpass filter, where basically we take, instead of the absolute value of s, we let it be absolute value of s for like some small region where we think all of our data that we care about, the frequency data that we care about is, and then after a point we make it go to 0. And so, and this is what is going to be sort of a low pass filter or a band pass filter, depending on your perspective. It's basically, we're not allowing any high frequencies, so that's definitely why it becomes a low pass filter. Band pass filter is usually where you're saying like this region of filtering, so I don't want like low, very low, but I don't want very high, and so you multiply by some sort of like square function. And in here it's not quite the same. It's basically absolute value of s that curves down, so we are still damping down low frequency content, but we're also killing any high frequency content. And so so basically the idea here is that we're going to go ahead and I'm going to show you what filters are, how to use them, and how to design them. And then we're going to, then for the next lecture, we're going to talk about, take a look and seeing how we can actually use this new idea of filters in order to invert the radon transform. In any case, that's enough blabbering. It's been 6.5 minutes, and so I'll let you get back to it. Okay, so let's go ahead and start. So what I've written up here is the filtered back projection, and one of the things that we're going to be talking about today is exactly what does filtered mean. Now there's actually a couple of ways to look at this particular problem, and before we jump into filters and other things like that, I was going to briefly mention one other interpretation of this formula, and in particular it concerns this particular piece. So if you take a look, we have f inverse of s times f of some function and of s. Remember the actual Fourier transform is only being taken with respect to s, and theta is just a fixed number throughout all this. So this is happening at some point x. Now there's this whole idea of fractional calculus out there, and there's a lot of the work out there, it tends to be unmotivated. There are a lot of operators that are introduced over and over again without actual like application. But there's a handful of them that do have good applications, and this is one of them. So the way to view this as a fractional order derivative operator, differentiation operator, is to first examine what is called the Laplacian. So if I were to take a Laplacian of a function g, that is basically a d by dx1 squared plus all the way up to d squared by dxn squared acting on g. And since we know that the Fourier transform of, say, d by dxi, or well, let's say xj, so we don't confuse the imaginary number with the index, of not just that, but say d by dxj of g, that is going to be minus I times wi of the Fourier transform of g. Here I'm actually using w as my frequency, so just put w there. Okay, so it's basically the wi'th component or wjth component times negative I. And so if I were to, say, apply this twice, so put a square here and a square here, then I'm going to basically get this out twice as well. So then if we actually square that, that's going to end up giving us minus wj squared times f of g. And then we can see that the the Laplacian itself, so if we take the Fourier transform of negative Laplacian of g, then this is going to be w1 squared plus all the way up to n squared times the Fourier transform of g. Okay, and now we can put absolute values in here, and then there we go. Now, if we want to talk about the fractional Laplacian of G, then that's basically going to be this. So we typically write it as alpha over 2 times G, and this is going to be basically going to give us back exactly what we see here. So this is can be seen as the norm of W squared, and so then this should give us norm of W to the alpha times F acting on G. So then, using this sort of definition through the Fourier transform, we can say then that the fractional Laplacian acting on G is just what you get when you inverse the Fourier transform, use the inverse Fourier transform on this quantity, the norm of, say, W or omega to the alpha, acting multiplied by F of G. And so this is called the fractional Laplacian. And in particular, we see that filtered back projection is using the back projection operator on the fractional Laplacian of the radon transform, where we take alpha to be just 1. And of course, this is also just in one dimension. So yeah, I mention this because I do a lot of work in fractional calculus, and this is a very big application area of it that nobody seems to really talk about much. So I thought it'd be worth mentioning, but today we're really going to be talking about filtering more than anything else. Now, what is filtering? Basically, on a high level, basically it's modifications on a signal, usually to remove or filter unwanted features, such as noise. So often you have some sort of function that is going to, basically look something like this, and you want to be able to get a clean signal out of this, but what you really get is something that looks more like this. And so you want to be able to get rid of this sort of thing that has somewhat of a high frequency, and so basically a low pass filter should get rid of it. So we want to kill high frequency noise. And this leads us to what we call low pass filters. Sometimes we also want to get rid of low frequency content, and then we'd use a high pass filter. So it does depend on the situation. In some respects, the filtered back projection is kind of doing some sort of high pass, but that's problematic because it amplifies our noise. So essentially, what you would get here with this, if you take a look at the Fourier transform, is you probably have some nice lower sort of frequency stuff, but then once you get to like high frequencies, you end up having some sort of spike here because it seems to be a lot of content. And so the idea is that, so this is the Fourier transform, this is just a cartoon of what you'd be seeing. We're basically going to take the Fourier transform, and we're going to multiply it by a function that looks like this. And this is the low pass filter. And so then once we multiply it by that, the ultimate Fourier transform that we end up getting is going to be something that looks like this. Now, having this sharp end right here is actually not technically possible. So often we have some sort of smoothing that's going on, like a polynomial interpolation or something like that. So we end up having something like this. But in sort of a hypothetical world, we would like to be able to give a sharp cutoff there, but sharp cutoffs lead themselves to high frequency content. So that's basically what we're going to be talking about, is how to design these sort of guys and figure out why they're good or not. Now, if you look at what's going on here, we're taking the Fourier transform of the radon transform and multiplying it by the magnitude of f's. So in this situation, what we end up having is we're multiplying it by a function that's doing this. So that's actually going to kill or really damp down low frequency content, practically kill anything you would say below some point. But anything that is high frequency gets dramatically increased, and the higher frequency it is, the even higher the amplitude is going to get, because we're going to be multiplying by something that's increasing unboundedly. So the goal of this section is to basically choose some sort of high frequency area where we want to cut off, and we're going to replace the absolute value of s with something like this. And so then, and that's going to give us, and that's basically the signal processing bits that we're doing here. So that's sort of the motivation of this section, and what we're going to do now is we're going to go ahead and talk about, how to imagine these sort of filters and the relationship to what is called convolution, because basically if you take basically what we're going to be doing is we're going to be multiplying our frequency content and by another function. And so if it turns out that you can represent say some g like this, then we know that this is actually equal to the Fourier transform of g convolved with, say, RF. So we're trying to find something that goes into place here. Right now we have absolute value of s, and it turns out that that actually doesn't have a nice inverse Fourier transform as a function. And so we're going to try to replace absolute value of s with some Fourier transform of some other function that we can then, that we know the inversion process actually happens just through convolution, so that way when we find the Fourier inverse of this product, it's just a matter of convolving functions that one corresponds over here and one that corresponds over here. Okay, and so then so we can do that whole Fourier inversion process, and with just some basic calculus like integration or something like that, and then apply the back projection. Okay, so let's go ahead and start talking about one example. I don't know why, but lately doing lectures I've been like pulling teeth. I don't know, I feel like my kids are getting more sophisticated, so I have to do all this stuff in tiny little pieces. In any case, so I took a break to get a breather. I guess I'm more exhausted than I realize by this whole pandemic. In any case, so back on topic. I'm basically following Feynman here, and so this is an example. Why can't I find it? So this is basically building up to example 7.1, and this is out of the Tim Feynman book. And so basically what we have is we're taking a look at this one filter, and it's called the moving average filter. And so this is f average of x is equal to 1 over 2t of the integral from x minus t to x plus t of f of little t dt. So, and the general idea is that you have some function f, and what we're going to do, or some signal, and so instead of taking the value at x, we actually use all the information around x and take its average, and this goes from x minus t to x plus t. And so we divide by 2t, the length of that little interval, and we have the integral here. So this could actually work as sort of a low-pass filter, and I think it actually is a kind of a low-pass filter if we take a look at the Fourier transform in a minute. But in the short run, the idea is that if f is varying a whole lot in this small region, taking the integral should kill any sort of high-frequency noise. Generally speaking, we think of a noise as having zero mean if it is perfectly random, and so integrating it should actually kill it. Kill any noise and give you back your true signal. I actually use that fact in my research quite a lot, and we might talk about that a little bit later. So So let's go ahead and talk about it and take a look at another way that we can represent this. There's another function we're going to introduce here, and this is going to be phi of t, which itself is going to be 1 over 2 pi, or 2t, sorry, of the square wave, which we're denoting by this upper little square thing, of t, at t, which itself is defined this way. So he defines this kind of backwards, and it's a little annoying, but all right, let's go ahead and do it. So basically it's going to be 1 and 0, and so it's going to be 1 if t is within negative, basically absolute value of t is less than t, and otherwise, so all of the values, it's going to be 0. So this is square wave, so we have big T and negative big T here, and on the inside of this interval, we're just 1, right? And this guy is a normalization where basically it says, basically it's chopping it down, or maybe blowing it up depending on how big T is, and this makes it so that the area is actually 1. So the square wave makes it literally 1 for pointwise, but on average, phi of t is going to make it the integral being 1. Okay, so and like he says, if you take integral from negative infinity to infinity of phi of t dt, this is actually just the integral from minus t to t of square wave of t at t dt, and that's 1 over 2t that. And so since this is just 1 identically inside the interval, that is just going to be the area under that curve is just going to be 2t, and so therefore this is just 1. Okay, so what we can do is we can make a few little adjustments, and you'll see that we're trying to build up to the convolution here. And so here we have phi of x minus t is then just going to be this. So it's going to be 1 over 2t or 0. And then we know it should be x minus t is less than or equal to big T less than or equal to minus t. And we want to think of this as some sort of, as a function of little t. And so we're going to think of these bounds as being x minus t is less than t is less than x plus t. So we're going to kill that, and this is all of the values. It's just going to be 0. Okay, so now we're finally going to write it like this. So we're going to take f of t times phi of x minus t, and then we see that if I take the integral from minus infinity to infinity here, dt, then what we get is not only f star of phi of x, but it is also going to be the same as writing 1 over 2t integral from x minus t to x plus t of f of t dt. So this is f average at x. Okay, so there we go. So basically I've just expressed this guy, our moving average filter, as a convolution with some other function that was just square wave. And so I know if I take the Fourier transform of this, it actually turns into the product of Fourier transforms, and that goes back to what I was just talking about, is that will feed into other things. And so what we can do for example 7.1, what he does in particular is he says, he says to assume that a is a real number, it's positive, such that a is bigger than t. And then we want to consider the particular case where we take f of t to be equal to the square wave of with a at t. Okay, so now the goal then is to basically we want to find f star of phi at x. So let's go ahead and start doing that. All right, so I'm going to draw an axis, and I'm going to draw a few things on here. So essentially what we're going to have is we know that this is equal to the integral from negative infinity to infinity of f of t times phi, I keep doing that, not curly phi, but straight phi, of x minus t dt. And in this case, we have basically the square wave at a of t times the square wave, well, I'm not going to write that, I'm just going to write phi at x minus t dt. And so, but this is also a square wave here. Okay, so what do we know? So to start, if this is 0, we're going to have our f is going to be centered like this. And then we're going to have this other guy, and if we just check our bounds, we have this phi of x of t as these bounds. T must be between x minus t and x plus t, and otherwise it is 0. So we're going to have some sort of window that we're going to be moving here like this. And so basically, and we know it's smaller than a. So this is going to be x minus t and x plus t. Okay, so there's going to be 3 different cases that we can consider. And so one case that we can consider is if we're entirely inside the minus a to a piece. So if x minus t, which we know is less than x plus t, is less than a, and this guy is less than minus a, what is that integral going to be? Well, we know anything outside of this region is just going to be 0. And otherwise, f is just 1, and this guy is just 1 over 2t. And so, so ultimately, what we get is this. We have the integral from minus infinity to infinity of square wave at a of t times phi of x minus t dt. And we know that this is the integral from x minus t to x plus t of phi a of t times phi of x minus t dt. But this guy is just entirely 1 on that segment. And so then this ends up being the integral of the square wave divided by 2t, which ultimately is just 1. So so we know that in this region, this is f convolved with phi at x. We get this. Okay, so then there's going to be another really simple case, well, 2 simple cases, and we could take a look and see what happens if I put this guy out here. And so if I put that guy out there, then what do I get? Well, if I say a is less than, say, x minus t, and thus everything else, this guy, anything outside of the square wave here is going to be 0 if it's outside of f's range, and yeah, and so since there's no overlap, you end up just getting 0. And you can also have the case where x plus t is less than negative a, and so this gives us f convolved with phi at x is equal to 0. Okay, so we have 2 regions that we've worked out so far. Let's put this in orange. So we know that if x is bigger than, say, a plus t, then we're flat 0, right? And similarly, if we are less than negative a minus t, we are flat 0. Maybe I should use a different color there. Running out of colors. Here, use this one. So we're 0 here, we're 0 here. And let's see, we can figure out what we are on the inside. We know we're 1, at least at x equals 0. But basically, if we are at the intersection of these guys being satisfied, then see, so basically if x is bigger than, say, negative a plus t, and x is less than a minus t, we're just 1, right? So so this is negative a plus t, and this is a minus t, so we're just going to be 1. Let's keep that symmetric. Let's move this dot over. Can I move that dot over? There we go. Yeah, there we go. Okay, so then the question is, what happens on the rest? Now, I'm just going to give you a little hint, and it's just going to be linear. And so, and there's a reason to think about that. And basically, this is supposed to be a moving average filter, right? And so we're basically on that interval, we're going to be averaging, more and more pieces that are just 1, and versus more and more pieces that are just 0. And so, as we move from here to here, it's going to be less and less zeros and more 1s. So it's going to be increasing to 1, and vice versa on the other side. And basically, I mean, you can see that with this. So if I put this interval here, what we get? Well, basically, we're going to have what's this? Is going to be x negative a is less than, or negative a is less than x minus t, but a is sitting between here, right? And so the interval that is basically what we're going to be taking is the integral of 1 over 2t over this region that is basically stops here and stops here. And so this guy is going to give us f star phi of x is equal to a minus x minus t divided by 2t. And so overall, we're going to get a plus t minus x divided by 2t. And so you see you have sort of averaging going on. Okay, and same for if you move this guy over to the other side here. And so then that's going to basically fill out those two regions. Let's finish that in green, because you can see that those are clearly that's clearly a linear function with slope negative 1 over 2t. Okay, so yeah, that's the idea. So basically, this is a piecewise linear function that you get when you take this convolution. And this is something that we're able to do without actually performing any Fourier transforms or anything else like that. But Fourier transforms also allow us to properly, think about these things as sort of as low pass and high pass filters, and will allow us to better understand what's going on. Okay, so if you look at Feynman's book, his section, let's change to a different color here. His section 7.2 is all about convolution. This is Tim Feynman's book. So, I mean, we've already talked about convolution, but just for completeness, we'll sketch out a lot of things like this. So we have this operation we call convolution of two functions f and g. We usually think of these as being in the Schwartz space. It is going to be equal to the integral from negative infinity to infinity of f of t, g of x minus t, dt, and this is for x and r. So generally speaking, we're sticking to just like one dimension, and that's because the Fourier transform itself is taken only over these columns from the sinogram, and so we're thinking of this as sort of a one-dimensional problem. Even though the attenuation function that we're trying to get back at the end of the day is actually a two-dimensional function in this case, or even three-dimensional. So yeah, that's what we got. Now, of course, I mean, we did all that construction of the Schwartz space, and that is to give us guarantees that this integral exists. This integral exists if the functions were also, say, in LP. which means that they'd be, say, the absolute value of the pth power, the absolute value of the function. If that is integrable, then this is a well-defined integration, and that follows by Holder's inequality. But just keep the overhead for this class down. I just talk about the Schwarz space where everything's rapidly decreasing, and so integrals are always fine. So then talking about convolution, so we've already said that the average function at x is equal to f convolved with that phi we were talking about before at x, right? And so this is going to be a common feature that we have. So just to remind you about some properties of convolution, we have f star of g is equal to g star f, so it's a commutative operation. We have associativity, for instance. We have f star of g star h is the same as f star of g starred with h. And we have linearity, so we have f starred with alpha times, say, g1 plus beta times g2 is equal to alpha f star g1 plus beta f star g2, and this is of course where alpha and beta are scalars and g1 and g2 are functions, and also h is a function, etc. And so all that works out, and then we have our shifting properties and things like that, and so Feynman goes through a process of demonstrating that, but we have those theorems in the past. But finally, one major thing is this, and so it's good to remind ourselves. So if we take a look at the delta function, f convolved with the delta function at x, this is equal to the integral from t equals negative infinity up to infinity of f of t times delta of x minus t dt. And remember, the delta function is the unit impulse, and so it is 0 outside of anything where this is not 0. So it's only non-zero when t is equal to x, and we consider having sort of this infinite spike at x, right? And so and this is the functional or the tempered distribution that would give us back f at x. So f convolved with the delta function evaluated at x is just f of x back, and so this is what we call sort of a filter with perfect revolution. So the delta function. Let's see, choose color. So the delta function is a filter with a perfect resolution, and that's because we can get the function f back. And so then section 7.3 talks about filter resolutions, and so the idea is that in this we have the spike. There's actually no ambiguity there. It's not like a triangle or anything else like that. It's not a true function, but basically the idea is that all the information in it is contained at x, and it uses this to get f back. You can get things that are like we've already talked about. We've talked about delta sequences in the past, where basically we're going to be using spikier and spikier functions, for instance, or even like the moving average filter, if as we take t to go into 0, gives us a delta sequence, and basically what the idea of that is that you're containing more and more of the area in a region around the origin for the delta function, and then when you use the convolution with that, it should produce the function f back to some extent. And so that lends us to talking about filter resolution and in a particular kind of function filters. So filter resolution. Right, and so here we're going to be talking about some concept called the full width half maximum. And so this is denoted FWHM. Okay, so generally speaking, so the idea is that we're going to have some function that is increasing up to a point, and then afterwards is going to be decreasing afterwards. And it doesn't have to be symmetric. It can increase up here and then go off, and as long as it's decreasing on the other side. So it increases, and then it could be doing something like that, right? And so the general idea is that we're going to be asking about the full width half maximum of this function. So that'll give you, and so so basically, let's go ahead and break down exactly what they mean about this. So so generally speaking, we are going to be so we're going to be increasing from on negative infinity up to 0, and decreasing on 0 to infinity for the cases that we care about. And so so this is a constraint that we have. So this is for the filters that we're going to be talking about, filters under consideration. And then he immediately breaks this when he goes and talks about other things, but we'll get there when we get there. So basically what we're going to be doing is we're going to be taking a look at those points where we have, say, if this is the maximum value m, and this is the m over 2, we're going to be taking a look at these points here and here, and this is going to be, say, x1 and x2. And so this is going to give us the distance between these two, x2 minus x1, is the was called the full width half maximum of, say, phi. And so this is what we'll call phi. So so this is a way of sort of compartmentalizing exactly how good of a resolution we have for our filters, and so the smaller that is, sort of the better reproduction of f we should get. And so for the delta function, we get perfect resolution, but the delta function isn't technically a function. So so we deal with these delta sequences, and as the full width half maximum of those delta sequences go to 0, we get better and better estimation of f through the convolution. And so so resolution is better for smaller FWHMs. And again, we saw lots of examples of this. We didn't have this definition, but when we were talking about all of our delta sequences, and so so basically, we can have triangles, tent maps that are like shrinking and increasing on the inside, as long as the average on the inside stays, the interval stays 1, then it ended up working out fairly well. If you hear all that scratching, that's my cats in the next room doing their business. Anyway, can never get quiet in the house. At least they're not howling this time. Okay, so he goes through and he talks about a few different examples here. So we have the full width half maximum of a box, and it technically doesn't. Sorry, there's the howling. Anyway, so again, we're taking a look at this box function, square wave, which is equal to 1 if the absolute value of x is less than t, and 0 if the absolute value of x is bigger than t. Put an equal sign wherever you want. And well, technically it isn't increasing it on either side, it isn't decreasing on either side, but people put this term, they make special exception here. And so the full width half maximum of this guy, t, is equal to 2t, and that is basically t minus t, and so it doesn't actually take any values
in the interim here because it's, well, a discontinuous function, but we think of the half point being somewhere in here. And so it's definitely bigger than 1 here and smaller than 1/2 here. And so we'll just say the distance between these two guys is 2t. So that's sort of an abuse, just to, you know, allow us to talk about this. The tent map is a little bit more well-defined. So basically what we have is we have, say, phi of t of x is equal to, say, 1 over t times t minus the absolute value of x if absolute value of x is less than or equal to t, and 0 if the absolute value of x is bigger than t. And so this is pretty easy to visualize. At x equals 0, you get t over t, so it's just going to be 1. And then outside of that, it's just linear. And then after it hits this point, it's 0. Right? So is that t and minus t. And again, we end up having then we see that 1 is our maximum value, and so 1/2 is half the maximum value. And so then, you know, this is going to be at t over 2 and minus t over 2. And so this distance here is going to be t. So the full width half maximum of phi of t is going to be written as just t. Okay. Is the difference between t over 2 and negative t over 2. So a little bit more interesting is the full width half maximum, the Gaussian. And so the Gaussian itself is going to be given as this. So f of w is equal to e to the minus bw squared. And we can go ahead and do that real quick. So if we go ahead and sketch this out, we're at 1, and it decreases down to this. And so the idea is that we're looking for, say, wherever we are going to be at the 1/2 mark. We know that this is 1 because e to 0 is 1. And then so basically what we're looking for is we're looking for f of w is equal to 1/2, say w naught if we want. And this is going to be equal to e to the minus bw squared. So then we just take the natural log of 1/2, and that gives us minus bw naught, say w naught squared. And so we get natural log of 1/2 over negative b. And we take the square root, plus or minus, as it gives us w naught. And so, and then all together, see, we can simplify this a little bit. So we get w naught is equal to either plus or minus, say, the square root of natural log of 2 over b. And so then the full width half maximum of f here is just going to be twice of the square root of ln of 2 over b. So, not too bad. Okay, and to round it out, Feynman also talks about the full width half maximum of a Lorentzian. And so that's basically, they're going to be taking a look at this function, GEW, is equal to t2 over 1 plus 4 pi squared t2 squared of w minus w naught. So it is a function that is centered at w naught. And yeah, so basically what we can find is that, well, it has this centered at the, so it has this centered at w naught. So not technically centered at 0, but if you did put w in for w naught, it is going to give us, say, g at w naught is equal to, say, t2. And so then if you want to find, and so we're just going to be thinking of this as sort of peaking there. And we're thinking, so in this case, we're thinking of w naught as sort of our 0 point. And so then the idea is then we're looking at, say, looking at some point, I'm just going to call it big W, that's going to give us t over 2, and so then it's going to give us t squared over 1 plus 4 pi squared t 2 squared big W minus W naught squared. And so then that tells us that 2 is equal to 1 plus 4 pi squared t2 squared big W minus W naught squared. And so you just keep working things out. So you get 1 divided by 4 pi squared t squared is equal to W minus little w naught. And so then that gives us a plus or minus 1 over 2 pi t2 and then plus W naught is equal to W. And so then basically you take W naught plus this and W naught plus this and W naught minus this, and you add them together, or you take their difference, and so then ultimately it gives you the full width half maximum centered at W of G to be equal to 1 over pi T2. Okay, so the book also mentions that these signals are important in magnet MRI, and T2 is called a relaxation constant. So we can, and hopefully we'll have time to talk about that later. Okay, so again, following Feynman, just to remind you, and I've already kind of reminded you of this, but basically, so this is section 7.4, and it tells us that we're taking a look at convolutions and the Fourier transform. And so basically, we have the big takeaway of this section is f convolved with g. If you take its Fourier transform, it's going to give you f, the Fourier transform f times the Fourier transform of g. Now, I think we also are missing a constant out here, and you can check the other lecture to square that away. Oh, maybe I shouldn't be lazy. Yeah, let me look that up. Okay, so I got off my lazy butt and looked it up because I couldn't quite remember. So if you use a Fourier transform, you don't put a normalization constant in front of it. This formula written here is exactly right. But when we did the symmetric normalization, in order to get what ends up happening with the convolution is you get 2 pi to the n over 2. And so in this case, since n is largely going to be 1, it's usually just going to be 2 pi to the 1/2. So, so there you go. In general, that is going to be one difference between the Fourier transform that we developed following the book Applied Analysis, and then coming back to this Feynman book. It's not a tremendous difference. Sort of morally, it's just splits the convolution into a product of Fourier transforms, and we can think of it like that as much as we want. This is just going to be some sort of normalization constant. Okay, so then moving on. So basically his whole 7.2 is establishing this, and we've already actually established it. So then we get into a little bit more interesting results when we talk about his section 7.5. This is something we haven't actually done yet. And this is called the Rayleigh-Plancherel theorem. Okay, and so basically we're going to say we're going to let f be an integrable function, be a square integrable function. Also, we're going to let f be an integrable function. And so then if either f or its Fourier transform. Which is curly f of f, is square integrable. Then so is the other. And more importantly, we have the integral from minus infinity to infinity of the absolute value of f of x squared dx is equal to, now I'm not certain if this constant holds for us anymore. We'll see as we go through the theorem what we need. We have, but otherwise we have the square of the Fourier transform. So basically, there's a direct relationship between the square integral of f and the square integral of its Fourier transform. Like I said, these normalization constants sometimes change whether or not you're taking a look at, say, the symmetric version of the Fourier transform or the or anti-symmetric versions. And so this might be subject to change. We'll come back and modify it after we get through the proof. Okay, so let's go ahead and take a look at the proof of that theorem. And so this is actually a pretty slick application of the convolution property. So if we take a look at the integral from minus infinity to infinity of the absolute value of f of x squared dx, and we think of f as a complex valued function, so then we have the integral from minus infinity to infinity of f of x times f of x bar, where the bar represents conjugate dx. And then this can be also thought of as the integral from negative infinity to infinity of f of x times f of x bar times e to the minus I times 0 x dx. So this is the Fourier transform of f times f bar evaluated at 0. Almost, actually. So in order to get the Fourier transform, we would have to divide by 1 over 2 pi to the 1/2, and so we're going to put 2 pi to the 1/2 up here. Okay. So now what I'm going to use is I'm going to use the fact that this guy, the Fourier transform of the product, can also be written as a convolution of the Fourier transforms. So this is going to be 2 pi to the 1/2 times, I think, 2 pi to the 1/2 again of f against f star f against f bar, and then this guy evaluated at 0. All right, so the convolution of those two functions. And so now we have 2 pi out here. This is sort of the converse of the formula we just talked about a second ago. And but in our case, it holds symmetrically. So that's what we get. Now, we have the integral from minus infinity to infinity of f times w times f of f bar of 0 minus w dw. And so taking a look at what this is real quick, so off on the side, let's do this in orange. We're going to have f of f bar at 0 at, say, negative w. And so this is the, say, 1 over 2 pi to the n over 2 times the integral from minus infinity to infinity of f bar of x times e to the minus negative w minus I w negative wx dx. Whew. Okay, and so this whole thing up here just becomes say x times e to the I wx dx. And now if I put a conjugate on this guy, I get a negative sign in here, and then I have a conjugate over everything, and so then I can pull that out. And so ultimately this is f of fw bar. So now I get 2 pi times the integral from minus infinity to infinity of f of fw times bar of f w dw, and altogether I get 2 pi times the integral from negative infinity to infinity of the Fourier transform of f of w and this guy squared dw. And that is the theorem. So this really just used the convolution property, and yeah, that's pretty handy. A note that Feynman mentions is that apparently Rayleigh established this back in 1889, and he assumed that both intervals were finite, and Plancherel was the one who proved that if one integral is finite, then the other one is too, and he did it basically through this chain of equalities. So yeah. Okay, so now for what follows, we're going to go ahead and talk about, we need to define what we mean when we say the convolution in two-dimensional space. And so he has a brief section here, convolution in 2D space. And so basically we're thinking of this in polar coordinates, because that's usually where these things are happening for us. So generally speaking, we're going to have two functions, f of t theta, and we're going to have g of t theta. And we define f star of g acting on t theta in the following way. We say is s is equal to negative infinity to infinity of f of s comma theta times g of t minus s comma theta d theta. And so convolution is only taken with respect to the radial variable. Right. And so this is going to be, and the reason why this is what we're doing is because, I mean, we saw through the filter back projection that we basically will fix theta whenever we talk about the Fourier transform. So we end up fixing theta, and then we just run over the radius for each one of those guys. Okay, but yeah, all the other ideas still stick in there, like commutativity and the application of the Fourier transform, and etc. Just because, well, the Fourier transform, generally when we're taking it, we're thinking really, again, only taking it with respect to the radial variable. So since this convolution is only applying to the radial variable, everything else works out nicely. Now, what we're going to do then is we're going to take a look at the relation between convolution the back projection, the radon transform, and the delta function. And this is section 7.7 out of Feynman. So to start off, we should go ahead and just define, reintroduce what the back projection is. And again, I am following Feynman here. And so this is the back projection on G is equal to 1 over pi times the integral from 0 to pi of G of x cosine of theta plus y sine of theta comma theta d theta. And so basically this takes a radial function and it looks at all the ways that you can match up with the coordinate xy and averages over them. And then if we take the radon transform of a function f of t theta, this is going to be equal to the integral from minus infinity to infinity of f of t cosine of theta minus s times sine of theta comma t times sine of theta plus s times cosine of theta ds. So basically for a fixed theta, it runs through the line. For a fixed t and theta, it runs through the line that goes through the radial point t theta. And it's perpendicular to that. to the ray that goes and matches it. Yeah, you get the idea. In any case, so there is a proposition here, 7.13, and basically, for suitable g and theta, i.e. Schwartz space functions, we get this. So, so for suitable g of t comma theta and f of xy, and arbitrary big X and big Y real numbers, we have the following. And so it is going to be BG, the back projection, acting on G, starred with F, evaluated at XY, is equal to the back projection of G starred with the radon transform of F, and this guy evaluated at XY. Okay, so, yeah, so that's the idea. Oh, sorry, I mixed up something. I thought I was a little wrong here. This should go out here, and this should go in here. All right, so basically the idea is, if you take the convolution of the back projection against G with F, it is the same as doing the convolution, the back projection of the convolution of G with the radon transform of F. Now, sort of as an aside, you can sort of get an idea of why the back projection actually did any good in the first place when it wasn't the filtered back projection. And the idea is that if we replace G, replaced with, say, the delta function, then we get, on the right-hand side, we get B of RF acting on XY, because the delta function convolved with RF is just RF. And this would have been equal to the back projection of the delta function against F, like convolved with F at XY. And so if this ends up being something that's, say, somewhat peaky, then maybe you can expect it to be to give a good inversion for F. And so if we see that the full width half maximum of the back projection of the delta function is actually somewhat cogent, somewhat small, then you can see it as being sort of a something with a decent resolution to apply to F. And in fact, we'll see that it actually turns out to be something that looks a lot like one of our kind of averaging filters. So then that'll be fun to talk about. But first, let's go ahead and talk about the proof of this theorem. Okay, so let's go ahead and take a look at the proof. So it's actually more or less what we've been doing up to this point already. There's some blue. And so we'll just start with one side. And so the back projection of G applied to F, it convolved with F, evaluated at big X, Y. This, just expanding definitions, gives us this. Is the integral from negative infinity to infinity and negative integral from negative infinity to infinity of, say, bg of x minus little x and big Y minus little y dot f xy dx dy. And so contrary to what we just talked about, and the previous one was radial coordinates, we're using the actual convolution that comes up with the two-dimensional, the actual two-dimensional case for just R2. We're not in polar coordinates. I don't know why the author decided to do that otherwise. But in any case, if we go ahead and expand G with the back projection, this is what we get. So integral from negative infinity to infinity, integral from negative infinity to infinity of 1 over pi times the integral from 0 to pi of g, and then we get a whole bunch of stuff in here. Big X minus little x times cosine of theta plus big Y minus little y times sine of theta, comma theta, d theta, and then this whole thing times f of xy dx dy. Okay. Now we're going to use the same substitution we keep using over and over again, and it's going to be x equal to t cosine of theta minus s times sine of theta, and y is equal to t sine of theta plus s times cosine of theta. And we've demonstrated that the Jacobian of this transformation is just 1. And so dx dy is the same as ds dt. And if we go ahead and employ that, just skipping a few steps, it's going to be 1 over pi times the integral from 0 to pi times the integral from minus infinity to infinity of g of big X cosine of theta plus big Y times sine of theta minus little t of theta times the radon transform of f at t theta dt d theta. Now, this is now our polar coordinate sort of version of our convolution versus the R2 version of convolution that we were used to before. And so then if we go ahead and we take a look, this is simply the same as this. 1 over pi times the integral from 0 to pi of g convolved with rf of x times cosine of theta plus y times sine of theta comma theta d theta. And ultimately this is the back projection on g convolved with radon transform of f evaluated at x comma y. And there we go. So so that's the theorem. So now that we've established that theorem, our next goal is to investigate this idea and figure out what the back projection of the delta function is, so we get an idea of why this should have worked in the first place, or even approximately. And so we're going to find that this ends up being sort of an inverse cone, and which basically it peaks at the origin and it decays fairly quickly, and so then it's giving us sort of an average version of our function. But yeah, we'll go ahead and talk about that next. Okay, so let's go ahead and take a look at what the back projection of the delta function is. So what we're going to do is, in the place of the delta function, we're actually going to use a delta sequence, and here Feynman uses the notation h sub a of xy, and he says it is 1 over 2a if negative a is less than r is less than a, less or equal to a, and it is 0 if absolute value of r is greater than a. So here, it's not xy, it's r theta, my mistake. Can't think right now. Anyway, so basically this is again a square wave. We're keeping it constant with respect to theta because when we're doing convolution with the polar coordinates, but like we said earlier, we're really thinking of this just as a convolution only with respect to r. And so we see that as a goes to 0, we maintain an area of 1, and then otherwise the that whole f already forgetting our own definitions. Our FWHM is going to be decreasing as well and going to 0. Okay, so what we're going to take a look at then is the back projection of HA of xy, and this is going to be equal to 1 over pi times the integral from 0 to pi of HA x times cosine of theta plus y of sine of theta comma theta d theta, and then basically what we're looking for is the only contribution we're going to really end up having here is when x cosine of theta plus y sine of theta itself is less than a, or less than or equal to a. So then redrawing this figure that Feynman has in his book, we're looking at basically a little circle around the origin, and this is going to be our point xy, and geometrically speaking, we are looking for those alphas that are going to make this work. And so we can see here, just by using a little bit of trigonometry, that the angles that are going to end up working for us are those that satisfy this, where we have sine of alpha is equal to a over the square root of x squared plus y squared. Now, as a goes to 0, we have alpha going to 0, and so basically that means that sine of alpha is approximately equal to alpha, and hence we're looking in the limit, we're going to be getting basically this. So the so if we consider both this ranging from say negative alpha to positive alpha, the overall contribution of this guy, of the integral, is going to be 2 alpha approximately equal to 2a over x squared plus y squared. Right. Okay, so because this is going to be sine of alpha. For small alpha, they should agree. So then that means that we're going to get this. The back projection of HA at xy should be approximately equal to 1 over pi times 1 over 2a, and that comes from the definition here of h, times 2a over square root of x squared plus y squared. And then we see that for very small values of a, which is what we want, we're basically, these 2a divided by 2a are going to cancel, and we're left with 1 over the square root of x squared plus y squared. Right, and so there we go. So this actually ends up being b of delta. So then what we can conclude as a corollary is that we get this. We get the back projection of the radon transform of f is equal to 1 over pi times 1 over square root of x squared plus y squared convolved with f of xy. And this is, when I write this convolution, I mean the typical r squared convolution that we had defined in previous lectures. So it's not exactly so I mean, like, if you look at this is basically something that it peaks at the origin. Just looking at a cross section, and then it's going to decrease this way. So basically this is what we're looking at. Anyway, so then since a lot of the content is contained around the origin and decreases as we go out, although it doesn't quite vanish, so that's its own problem. The most of the content, so that's why we get somewhat of a good representation when we use this method, but it isn't perfect. Okay, so next we should talk about filters and low-pass filters. This isn't going to be a long discussion, but it's important because it allows us to replace the magnitude of S with something that will actually allow us to work with a good approximation of the function itself. Okay, so now we're going to jump into some proper signal processing. And so we're going to talk about low-pass filters. Okay, so like I was saying before, essentially, if we take a look at the filter back projection algorithm, which is 1/2 of the back projection times the inverse Fourier transform of the absolute value of S times the Fourier transform of the radon transform of F, and this evaluated at xy should give you f of xy back. So essentially, this is what we're hoping would be actually is what we're going to call a filter. And so if there existed, say, some phi such that the Fourier transform of phi gave us the absolute value of S, then what we would find is that we can use the convolution property to say that f inverse of the absolute value of S times f of RF is equal to basically phi times the convolution of the radon transform of F, right? Times, some constant here. And so, but the problem is that there is no function that satisfies the Fourier transform of phi being equal to the absolute value of S. And so we're sort of hosed there. But we can replace the absolute value of S with something else and still get a good approximation. And in general, because absolute value of S gets really arbitrarily large for large values of S's, that means that if we have high frequency content coming in from noise, all that noise is going to get blown up considerably. So even in a perfect world, since RF is coming from data, if there was a way to do this, you probably wouldn't want to do that anyway, just because you're going to be getting a lot more input from your noise than what you'd like otherwise. So then the goal is to find we want to find a band limited function that we can use in place of absolute value of S. All right, and so let's talk about what a band limited function is. All right, so our definition of a band limited function is this: a function phi whose Fourier transform is non-zero on some finite interval and 0 outside the interval is called band limited. So basically we're saying that if you have some sort of function phi, whatever this is, if you take its Fourier transform and you take a look, and so this is the time domain, this is the frequency domain, and basically it does something like this, but in a 0 outside, this is called band limited. Right. And generally speaking, this is if these are going to be what are called low pass filters, because for higher frequencies they end up killing any high frequency information. So the only thing that passes through ends up being lower frequency, or at least within this band, which would be a band pass filter technically. So so a couple of little things. So it turns out that if your Fourier transform is band limited, another thing mathematicians call it is we say that it has compact support. Then it turns out that phi itself has to be an entire function, a complex entire function, and vice versa. And so then that tells you that. And another thing that we can take away from this is that you have this relationship between Fourier transforms of functions and the original function itself, and that since this has now we saw before that decay feeds into sort of smoothness, and so here we have sort of perfect decay where we're zero outside of the region, and so that leads us to having entire functions which are sort of as smooth as you can ever expect to find out of a function. And so yeah. Anyways, so our goal then is to design some of these bandpass filters, which are ultimately going to come down to being entire functions. And so if you are familiar with complex analysis, there is this connection there. So to design a low-pass filter, to replace, say, absolute value of s, we're going to follow the book and basically introduce a function like this. So we're going to have AW, so this is in the frequency domain, and we're going to have the magnitude W, which say magnitude of s, times some other function, we don't know what that is yet, times the square wave, where we want to chop it off. And so L here is just some real number, positive real number. And so then because the square wave is zero outside of L, that means this function will identically vanish. So typically we're also going to want to keep some nice properties about the function. So we want f of 0 to be 1, and also we want f should be even. By selecting f even, that basically means that the Fourier transform, the inverse Fourier transform of this function a, phi, is real valued. Okay, so then let's talk about three different ones that are typically used. And so first you have the Ram-Lack filter, and this is pretty much the first thing you would try. So basically it's going to be the absolute value of omega times the window function here, times the square wave, and that gives you W in absolute value if W in magnitude is less than or equal to L and 0 otherwise. Right, so this is just sort of a hard cutoff. But hard cutoffs can lead to a ringing phenomenon, and so often people try to go and get rid of this by using some functions that are continuous as they approach the boundary. So this guy is basically just doing this. And so we're going to try to choose some other guys that are going to be nice and smooth and continuous as we approach that boundary. So the next one is the Shep-Logan filter. It's a capital L there. And so this one denoted by A3 in the book is equal to the absolute value of W times sine of pi W divided by 2L divided by itself pi W over 2L, and this times the window, the square wave here. So then ultimately what we get is we get this interaction between W and the absolute value of W. Remember, this is just a single variable, and so what this ultimately gives us is 2L over pi times the absolute value of sine of pi omega divided by 2L. And this is for absolute value of W or omega less than L, and otherwise we get 0. Okay, so that's a little bit easier to put our head around. So basically, once W gets to be L, we're going to be at pi over 2, and for sine. And so if sine is pi over 2, then let's see, what do we get? Yeah, so then what we end up getting is we end up having being up at 1, more or less, or well, actually 2L over pi when we get up to 2L, or when we get up to L. And so ultimately this looks like this. So it's almost like what we had before, especially locally it's here. But then again, we have another hard cutoff. And so again, that could lead to some ringing phenomenon where we're trying to invert it. And so there's other ways, other things we can keep looking at. And so the last one is the cosine filter. And what this is defined this way, and for some reason he chose to put this as A2. And so this is the absolute value of W times cosine of pi W over 2L times the window, or the square wave of size L. And so yeah, this gives me this absolute value of W times cosine. Well, you get the idea. Don't need to rewrite all that stuff. Basically, it's 0 outside the origin. Nothing funny happens here. What made me hesitate here on this last one is I was expecting it to go to 0 when we got down here. I expected it to do that. Just because I knew that one of the signal processing things you try to avoid is sharp cutoffs. Because that can lead to ringing and other things. And so, but that's exactly what this does. And so when you take a look at this guy, that's what's going to end up happening. So cosine, we know it starts up here and then goes down like that, but since we're multiplying it by absolute value W, basically that guy is going to be multiplied by cosine, which is 1 here. And then when we get up to L, we're going to be looking at cosine of pi over 2, which is 0. So essentially, this is what ends up happening. Get a little McDonald's logo here. And then 0 outside of that. Now, if you were to take a look at these 3 different ones, the one that closely matches the absolute value is this one. And then this one is sort of a little bit worse, but it's different. And this one actually vanishes at the other endpoint, but it matches the absolute value function the least out of these 3. So we can play around and see exactly how well each one of these does in the upcoming projects. Okay, so I'm going to end up stopping here, and yeah, this has been well, a full lecture. All right. Thank you for listening, and I'll see you back at the office. Okay, so that's that. So now you know what filters are, and yeah, so now the rest of these lectures are going to be committed to finding ways of actually implementing them.
And so next we're going to start look at things like the discrete Fourier transform and other things, because we are always dealing with discrete data. And so so this is the next step on our journey. Anyway, thanks for watching, and yeah, I'm excited to get into all this with you guys. And thank you for being patient. All right, I guess I'm gonna stop there. All right, take care.